we will be implementing our model in the RTLab software. So now to first of all we need to open our MATLAB model. This is the already prepared MATLAB model. Now we have to make sure that our MATLAB model is compatible with the RTLab software. So we will have to make few changes in our model. First of all, there should be only two subsystems in our model so that it's compatible with RTLab. So first of all, I have converted our model into one subsystem. As you can see, our model is into one subsystem, and this is called as a system subsystem. So rename this model into SM_subsystem. Now we are getting the stator current as an output. We need to observe the stator current in the real-time simulation. So we will get the stator output as the current from the subsystem. For that we will get the output now there are some restrictions in the OPAL RT. It can show output which range between -16 to 16, but the output we are getting of the current is more than 16. So that so we have introduced gain of 1/10 so that it is reduced by 10. So now we are giving the output. As you can see, now we can take the output from the subsystem. We are inserting the power GUI, and now we have to make sure that it is the parameters of the power GUI configured from continuous to discrete, and make sure the sample time is 50 e power -6, 50 micro. Also make sure we go to the simulation configuration parameters. By default it will be variable step here. Make sure you convert into fixed step, and the fixed step size should be equal to the size you gave, the sample time you gave in the power GUI, which is 50 e power -6. Now introduce a scope in this. Now, as I earlier said that there should be only two subsystems in our model, put the scope in the subsystem. This is the subsystem containing our scope. Now we have three output from this subsystem, so we will introduce input in this subsystem. Now we will mux the three outputs. Now you can connect the output from this subsystem to this subsystem. Now this is our subsystem, so we named it SM_subsystem. Now this is our scope subsystem, containing our scope, so we will rename this as SC underscore subsystem. Now the reason we are renaming this subsystem as the RTLab software takes this name by default, and it will directly detect our subsystem, as in which subsystem our model is there and in which subsystem the output scope is there. Now as you can see, our MATLAB model is ready to be simulated in OPAL RT lab. So we will save this MATLAB model. Remember to close the MATLAB before opening the RT lab. We will close the MATLAB software. Now open the RT lab software. Before opening the RT lab software, make sure the RT lab hardware is connected to your PC via LAN cable and it is on. Now we need to define a target. As you can see here, a target name VIT is already defined. If it is not defined, you have to go to the new and define a new target. Here you have to give the name, for example VITCC, and here you have to give the IP address, which will be the IP address of your OPAL RT. As it is already been given here once, RP address, we are not doing it again. Now this is the status of our target. The up indicates that the OPAL RT is currently connected to our software and it is ready to take the commands. If it is if it says down, click on the right click on the VIT and refresh the target. Make sure that the target is activated, is in up status only. Then only you can proceed further. Now we have to send our combine our MATLAB model with the RTLab software. So we'll go to new project. Now before going to this new project, you have to go to C, where you have the RTLab workspace. Here you will have to create a new folder and name the folder with the name, by the name you want to save your project. Say project. Now you have to remember this name, and this folder should contain 3 files. First 2 files you can, where you have installed your OPAL RT software, you can get 2 files from the needed files test models. These 2 files is needed to run the RTLab hardware. Make sure these 2 files are present in this project folder, and the third file should be the MATLAB model. Make sure that these 3 files are already present in this folder before you introduce this project into the RTLab software. That you gave in that folder, the same name you should give here. Make sure the location is same as the project, that folder location, and click on finish. Here the project, if you see here, the project is there and models. Now you have to combine the MATLAB model. So go to right click on models, add existing model. You click on link, browse, and browse for your model. Finish. Now here if you can see, the model is combined with RTLab. Double click on this, this will appear. Now we have to make some editing in the model so that you can run in the RTLab. When you click on the edit, automatically the MATLAB model will open. Now you have to make some changes here. Open the system subsystem. Now here you have to include these 2 blocks. First block is op control. Go to the simulation library. go to the RT lab, IO, input output, OPAL RT, common, op control. Introduce this to the subsystem. Now op control, double click on the op control. Now here you have to, these files which you introduced, rename, click on rename and copy this. Now in the op control block, paste this file name as .bin, and don't forget here the board type by default will be VC707, but the OPAL RT hardware we are using is OP4500, so we will change to OP4500. Make sure you change it to the as per the specification of the OPAL RT you are using. Click on OK. Now error and ID you have to introduce the terminator. Now we are sending the output from our model to the hardware. So we are sending the analog output from our PC to the OPAL RT. So we will have to introduce a block name analog out. You can get this block from the same RT lab input output, OPAL RT, common, analog output. Introduce this to the subsystem. Double click on this. Now analog output port contains 16 pins. First 8 pins are data in port number 1, and pins and the next 8 pins will be in the data port 2. Here we are using the data port number 1, and now we have 3 outputs. We are sending 3 outputs. As it is 3 phase, we have 3 phases, so we are sending 3 outputs. So we will be using 3 channels of the analog output. So here we are mentioning 3 and we are clicking OK. Here you can select the voltage range. As you can see, the maximum range is -16 to 16. So make sure the output you are sending is between this range only. If it is high, make sure you introduce gain and reduce it by the number of times, so that it is not less than -16, it is not greater than 16. Click on OK. Terminate this and connect the input through mux. Now here you can see this. We have taken the 3 stator inputs through mux, and we are giving this mux to analog output. Now you have to make one changes in the scope subsystem. As you can see, we have introduced this block called opcom. You can get this from simulation library, RT lab, opcom. Introduce this opcom, double click on this, make sure it is equal, this is equal to the number of the outputs you are giving. Click on OK. All the outputs you want to give it to the scope should be through opcom only. Now this model is ready to implement in the RT lab. Save the model. Now our model is ready. Now set the development properties. Here it is Q and X, change it to red hat. Go to overview again and now build the model. we have built the model, now we have to assign the target, this model to our target. So click on assign targets, click here in XHP mode and make sure that the target is, you can see the target here. If it is unmarked here, make sure you mark this clean target just to be safe. Again go to the overview. Now we have to set the execution parameter. Now we have synchronized our model with the hardware, so make sure this is the target platform is Red Hat, real-time simulation mode is hardware synchronized, and real-time communication link time is don't change anything else. Go to the overview. Now we have to load the model into the RT lab, OPAL RT hardware. Now we have loaded the model. Now once I click execute here, you will be able to see the output in the MSO, and you will be able to observe the waveform and get the output parameters, observe the voltage, observe the current, the magnitude, observe the frequency, and you can note down the observations from the MSO readings. We will be implementing our model into the real-time simulation using the OPAL RT controller. This is the OPAL RT controller OP4500. We have developed one model in which, and now we will be implementing in real time so that we are able to observe the transient in real time. Now I will show you how to convert the model so that it is compatible with this OPAL RT, and how to get the output using the OPAL RT software. We had loaded the model in the OPAL RT, and now we are ready to execute our model so that we will be able to see the output in our MSO. Now when he presses run, the output will start coming in our MSO. Here you can see the output is coming. Here you can see the output is there. So now we can change the frequency, measure the frequency, measure the peak to peak value, also see the change. Now in our model we had made changes in our input conditions so that the change is to observe this change. Now we can see the change in peak to peak value, measure the frequency. We can measure it at any point we need. We can measure at the point of transience. We can measure the different values. We can also save the results in the pen drive, and we can save our output results, and thus we have successfully implemented our MATLAB model into the real-time simulation. You saw the successful implementation. Now we are measuring the values, peak to peak values. Now here you can see the current values is 17. It shows volt as the MSO shows the current as volt, but it is actually measuring current. Now if you remember, we had introduced gain in our model part, so to reduce the output by 10 times. So here actually our output is 17 into 10, 170. Now when you can see, now when the load is reduced, you can see our peak to peak value changes to 11. Now this value is also to be multiplied by 10, so it is actually 110. So you can also measure different values by using this MSO. We can also measure the frequency. As you can see here, we have measured the frequency, which is If you can see, it is 50 hertz. So we can measure different values for our observation. This time we have measured the phase difference between the two phase. Now we have used the channel number 2, 3 and 4 of the MSO, and if you can see the phase difference between 4 to 2 is 120, minus 120, and 3 to 2 is 120. So the phase difference is also exactly 120. So we are getting the exact output we needed, and we have successfully implemented the model in the RT lab.